I'm gonna run it. I'm usually not a compliment. I thought it was good.
They have to get it,
Yeah, but like this, I just bring it right for you.
Okay, let me talk about this week for a bit. We're gonna finish up our notes hopefully by today. And we'll spend the next few days reviewing for our first test for the unit, which is just going to be the non-calculated portion. And so I'll give you a test review packet tomorrow. We'll work through it. We'll maybe do some calculator work in preparation for next week. So if we can have a graphing calculator by Wednesday, that'll be great. We can start looking at some of the features that we need to be able to know. Now on this, the calculator portion, I will give you a summary sheet. So, you know, you can kind of begin to, if you forget some keystrokes, you can use that as a way of kind of remembering, kind of help you through those process. I'm also going to do some help sessions over the course of this week. So between Tuesday and Friday, I'll have either morning or afternoon help sessions, and I will send out a reminder today, and each of these will be available on Teams. So I'll send you a text remind where you can just click on that link and just come into that Teams meeting if you want to join in. I'll also record each of these sessions as well. Okay. So let me do a little bit of review with U substitution, and then we'll talk about change of variable, and we'll look at U substitution with definite intervals and a little bit more notes that I have for us. Okay, so okay, so we talked about how anytime you see an integral anti-differentiation problem, you always want to consider your first option being power rule. Can I just use the knowledge that we have from the previous quiz, expand, clean everything up, separate every expression, no multiplication between any of the variables, and then apply power rule. Okay, so we always want to look for that as our first option. Now, if that fails and we realize that either power rule is too inefficient or it's not possible because of order of operation issues, then our next option is U substitution. And the whole point of U substitution is we want to take a complicated problem, introduce a different variable that represents a big chunk of the problem, and we're able to get this cleaned up to look like an easier problem to solve. We solve the easier problem, and then we bring back the original variable. Okay. And an indication that your U substitution method will go smoothly is if you pick a U value that has an exponent that is higher, 1 degree higher than the remaining variable outside the U value that you're trying to remove. Okay, because through power rule, you're going to able to get those 2 degrees to match, and then things should work out to allow you to reduce. Okay, so we worked through those problems, but I want us to explore this type of problem now. So this is example 7 on page 8. Briefly, we did work through example 6, where parentheses did maybe cause you to consider U substitution, but we always want to look for expansion first. So looks like that, if we just remove the parentheses, we're able to make it into a problem that we can just expand and then rely on power rule to solve. Okay, so example 7, we're going to run into a bit of a roadblock, but let's see if we can kind of reason our way through and find a workaround with this roadblock that we're going to see. But first things first, for example 7, are we able to expand this problem out and rely on power rule? I'm able to distribute that x through this radical. Okay, I can't. Okay, now because there's addition and subtraction inside, we would have to resolve the radical first, which we can't before we can distribute the x through. So let's look at U substitution. rewrite the problem. The radical can be rewritten as what? X plus 3 to the 1/2 dx. Okay. Can you guys foresee what issue we're going to run into? Yeah, the degree is not as clean as we would like, right? We know what our potential U value is. Our U value is that expression inside the parentheses. But this will be an easier problem if this is x squared plus 3, because then we know the derivative will cancel out with this x. So we know that this x is not going to go away as nicely as we would like. Okay, but let's still go through this process as far as we can go and see if there's something in the problem that can allow us to work around this issue. Okay, so our U value is x plus 3. Du dx. What's the derivative of x? 1, and 3 goes to a 0. Okay. Cross multiply, solve for dx. All right, so dx is simply just du. So we make our substitution. X stays. Parentheses becomes u. Dx becomes du. Okay, so I want us to understand that we are stuck. Okay. I see some students who see this problem and they feel like they can do this. They see the x and they say, well, okay, I'll just do power rule here, and I'll just do power rule here, and I'll just end the problem there. Okay, so we can't do that. Okay, and now this is an x plus. Maybe we can work around that issue, but that multiplication prevents us from being able to. Okay, we can't treat those two separately. Okay, so this is an issue that we have to resolve before we can go through with our antiderivative rule. So we know the x is not resolved. We can't move forward unless everything's in terms of u. So is there something in the problem that can allow us to work around this x that's getting in the way? Right, so we have something that we can play with, right? We have this equation, u equals x plus 3, that maybe I can find a way to get that x to be replaced. Right? So what if we can rearrange this equation? Right? So if I rewrite that equation, I can say x equals what? X equals u minus 3. So this is a kind of a way to work around the variable that doesn't go away, right? We're kind of looking to see if there is something available for us to play with. And this is called the change of variable U substitution, where your initial round of U substitution doesn't quite get where we want to be. So we have to look for another set of substitution to further get that x to go away, okay? Because we can't do this. Okay, so we have to continue to get that, find a way to resolve that x. Okay, so let's see what happens next. We're going to replace that x with u minus 3. Okay, so we're still not there yet. We can't quite do power rule, but at least we have a path towards something that we can do, right? So if I want to do power rule with this problem, I first would have to do what? Distribute, right? So, but this we can do, right? Before we couldn't distribute through, but now this is something that we can work with, right? We can distribute that u to the 1/2 through the parentheses, and there's no radical, there's nothing that's getting in the way, preventing us from being able to distribute. So let's expand this through. Okay, so u to the 1/2 times u to the first power, I do what with the exponents? Add, so 1/2 plus 1 is 3/2. Okay, so now it's a nice, clean power rule problem, right? More manageable than what we began with. So now we go through power rule. Okay. So add 1 to the exponent, divided by that exponent. Okay, flip those fractions in the denominator. Okay, we can do some cleanup, make that second fraction reduce, but we're still doing U substitution, and we have to understand that U is just a what? Yeah, just a place. It's just a temporary variable, right? We still have to bring our problem back in terms of what? In terms of X, right? So I think for some reason I feel like these are types of problems that students tend to most likely leave their answer in terms of U. So just keep reminding yourself that if your final answer is in terms of U, bring it back in terms of X. Okay, so just keep that in mind. I mean, it's a relatively minor mistake because you did all the calculus. You know, if you leave your answer in this form, you're still getting the vast majority of the points. But just remember that you shouldn't be leaving your answer in terms of U. You got to, you know, we started with X, we want to end with X. Okay, you can leave your answer either in radical form or leave it as rational exponents. Either is fine. Okay, example 7, example 8. Okay, so first thing we notice, we can't distribute through. So let's rewrite the problem with parentheses. And what do you think our U value is? Yeah, the 2 minus X. I know you're looking at that X squared feeling, this feels like could be a better fit, right? Because the derivative will match up with this X, but this is the more complex expression, right? You got that radical here, you have that expression here. So it feels counterintuitive because you're hoping for a degree that is higher, not less. But you know, now that we have this change of variable option, we can more easily, you know, have a bit of a safety net in terms of when your X's don't cancel out. Okay, so always target your parentheses first. All right, that's going to be usually the safer bet. Okay, derivative du dx. What's derivative? -1. Okay. Cross multiply. Okay, dx equals -1 du. We have our parentheses replaced. So let's see what we have. X squared stays. U to the 1/2 times -1 du. So the X squared doesn't go away, but we know we can at least target X, right? What can I replace X with? Yeah. X equals 2 if I move the X over to the left side and move the U over to the right side, X equals what? 2 minus U. All right, so there's more cleanup that's needed than what we had before, but at least we have a path to our answer, right? We can't quite distribute the U through, yet, but if we expand this out, we should be able to distribute that u to the 1/2 through without breaking any algebraic rules, things that we're able to do here that we were not able to do before. So I'm going to expand that 2 minus u squared out. I'm also going to just put the negative u to the 1/2 in front. I think I'd like to distribute with my term in front. So make sure that you spend the time to fill this out. Don't distribute that 2 through and forget about that middle term. So I pulled the -1 and the u to the 1/2 in front. Just visually, I think it's just easier when we're trying to distribute a single term through the parentheses. Put that in front rather than at the end. But now we can, we still can't do power rule yet, but we're working towards it. Distribute that through, then the parentheses should go away, and every term should be stand alone, and we can apply power rule to each term. And I'm keeping track of that negative, right? That negative that came out of the derivative process. I don't want to lose it, so put it in front as a way of reminding me. What's my next exponent going to be? 1/2 and 1 gives me 3/2. 2 and 1/2 gives me 5/2, right? 4/2 plus 1/2. Okay, so now things are cleaner, right? Every term is ready for power rule. We apply power rule, drop the integral in du notation plus c after them. And then once you divide by each of the fractions, you're going to flip those fractions up to the top, combine with the coefficient that's sitting here. And then don't forget, we still want to get everything back in terms of what? X. Okay, all right, so try that. See if you're able to finish off this problem. Okay, all right, let's check our answer here. Add 1 to the exponents, 1/2 becomes 3/2, 3/2 becomes 5/2, 5/2 becomes 7/2. Flip all those fractions to the denominator, and then bring those denominators up. So 4 and 2/3 gives me 8/3. 4 and 2/5 gives me 8/5. 7/2 flipped would be 2/7, and then all the u's gets replaced with the original x variable. Okay, so okay, we're gonna put some things together. U substitution with definite integrals. So if you guys can go turn to page 9. Okay, so U substitution with definite integrals. I feel like these are even more tempting where students want to just involve the 1 and 2 first. But again, we got to make sure that we treat these problems without the definite integrals first, right? We want to get everything resolved before the bounds can come into play. So there's 2 ways that that we can apply this problem. I think that there's a way that you guys are going to prefer, which is fine. But I want to show you another way because sometimes AP exam kind of forces students to see if they can work through a problem like this using the method that they prefer. So as long as you're familiar with both, you can make the adjustment. Okay, so first things first, let's rewrite the problem without the bounds so that we're not looking at the bounds because it's not going to play a role until much later in the problem. We have to deal with this problem first before the bounds have anything to do with our problem. Okay, so whenever you see a definite integral problem, pretend like you don't see it. Okay, that's as much as you want to read from left to right. We really need to just remind ourselves that the bounds is the very last thing that you touch. Okay, so we have this problem in front of us. Remember, our first option is always power rule. Is power rule possible with this problem? And the answer is yes, but what? Yeah, it takes a little bit of time, right? That anything that's higher than the 2, we typically want to just find a better way, right? It's not too bad, but it would take a little bit of time to expand all the way out. But it's doable, right? But potentially a better method. I also want us to practice with U substitution. So we can target what is our U value? S squared minus 2. Is this likely going to work out pretty well? Yes. So we'd like to see that. We'd like to see our U value with 1 degree higher than the remaining X outside the parentheses. That kind of gives us, just a feeling that, okay, things will work out. It won't drag out like the change of variable problem. So yeah, let's target our U value there. Okay, du dx derivative is 2x. Okay, make our substitution. Dx is replaced with du over 2x. Right, we can't move forward with U substitution unless all the x's have been resolved and removed. Are the x is going to go away nicely? Yes. Okay. Not only that, but the coefficients also went away. They didn't have to, but it's just nice that we don't have to worry about any coefficients. Okay, u to the third du becomes what? Okay, u to the fourth over 4. Now, this is where our paths will, so we have a couple of options, right? Because we've gone potentially as far as we can go without, now we can consider the bounds, right? Because we took the antiderivative, and then after we've taken our calculus step, we can now involve the bounds. But I want to talk about 2 ways that we can do it, and then a third way that is incorrect, right? And I want to talk about the incorrect way because it's easy for students to kind of fall into that option. So here's the first option. Okay. I'm gonna put a box around this because we've gotten through the indefinite integral portion, and now we're trying to figure out how do we work in that 1 and 2. Okay. So this option is I want to call this the College Board way, because they like to do things this way, and it's important that we understand this method because sometimes they will force a situation in multiple choice questions that ask the students can work through this method. But if it's free response, you're welcome to do any way you like. Okay, but I want to kind of show you here. So we want to involve the bounds, but can we involve the 1 and 2 as the way as it stands with this U variable? Okay. This is in terms of U, but these bounds are still in terms of what? It's X. So we have to get matching variables, right? So this is where the two options come in. Either you get these two matching in terms of U, or you get both of these matching in terms of X. Either way is fine, but what you can't do is you can't use X's with U's, right? Because there's a mismatch of variables if you do that. Okay, so okay, so this method is convert the bounds in terms of U. Okay. So the way you convert the bounds is you're going to rely on your assigned expression that you built. Okay, so that U equals X squared minus 2, that's gonna be how you're going to convert those bounds. So we can say if X is equal to 1, then the U must be equal to this conversion here. So if I replace 1 in for X, what do I get? 1 minus 2 is okay, negative 1. Okay. If X equals 2, right? If my upper bound is 2, I push it through the conversion. What's my new converted U value? 4 minus 2, which is 2. So now you have your adapted lower bound and you have your adapted upper bound. So now you're ready to work the problem through. U to the 4th over 4, bracket, half bracket. Your lower bound was 1, and now your new lower bound is negative 1. Your upper bound was 2, now your new upper bound is 2. Okay. Looks like the conversion didn't change the value, but we did get into a different variable. That's what's more important. Okay. So now you got matching variables. Your antiderivative is in terms of U. Your bounds is in terms of U. Okay, what gets inserted first? Okay, upper bound. Okay, or the top number. Okay. Then the lower number here. So 16 over 4 minus 1 over 4 is 15 over 4. That is how we go through definite integrals, find definite integrals with U substitution stuck in that process. Now, I want to point something out here. Sometimes your conversion may push your lower bound to be lower or higher than what was initially this relationship, right? It's possible that through this process, this lower bound all of a sudden became higher than upper bound. If that's the case, don't try to overthink it, right? So whatever starts as lower bound, it's going to end as lower bound. So even if this value ends up being a 10 or 12, this is still going to go in second. Okay, so whatever number is up here is going to go in first, even if it suddenly changes, so yeah, so whatever starts as lower bound, you're going to keep as lower bound. Whatever you start with upper bound, you'll keep as upper bound. Things will work itself out. We don't have to worry about making that adjustment. You know, if this U substitution process forces this to be a different order, just work through with that different order. It's okay. Okay, the second method, which I think most of you will prefer, which is okay, but this is, I did definitely want us to be able to be familiar with this method. So basically on the test, if you always choose to do, I'm not going to ask you to do, I'm not going to ask you to do one method or the other method. You can always choose, okay? And I'm not going to ask you to work a problem with both methods, okay? But as we practice, I will have you guys, maybe practice with both methods. So the second is, instead of converting the bounds, we just bring the u back in terms of what? X, okay? So we bring this back in terms of x. We have x squared minus 2 raised to the 4th over 4. Okay, so here we have our antiderivative in terms of x. And if we do it this way, then we can just rely on the original what? Original bounds. Okay, so I think most of us prefer it this way. The advantage of this is you go through the process like you normally would, and you just plug in the bounds when you're ready to involve x's. The downside is that you're working with a more complex expression because with this method, you kind of front load your cleanup effort a little earlier. And so when you get to the end, it feels a little bit cleaner to work through. Right? But it does expect you to do, some more additional steps at the beginning. Okay, so upper bound first. Then lower bound. Okay, so 4 minus 2 is 2, to the 4th is 16. 1 minus 2 is negative 1 to the 4th is 1. So 16 minus 1 is 15. We get this same answer. Okay. And then number 3, this is an incorrect method. Okay, we can't do this. We can't take that u to the 4th over 4 and then use the bounds that is not adjusted. I know that this ends up giving us the same answer, but that's not the correct process, and likely you're not going to get the same answer each time. Okay, so make sure that you either get everything in terms of x or everything in terms of u, but I can't have one in terms of u and the other in terms of x. Okay, let me come back to example 2 a little bit later. This process makes sense. Right, so really, we're taking what we already know, we're just pushing it a little further and understanding that there's an incorrect and correct way to work with the bounds once you find your antiderivative if there's bounds involved. Okay. All right, let me see if I can get through this last page of notes here, page 10. Even and odd functions. Okay, we'll skip the review for now. And let me talk about even and odd functions and even and odd rules. So an even function is where you can look at the graph and the graph looks like they're mirror images of each other on either side of the x-axis. So if I can take my graph and fold it over the y-axis and everything lines up, that is an even function. So if there's an area of region 3, then an even function is going to mean that there must be an area of region 3 on the other side. Okay. So the rule just says if I take half, or if I take the full interval it's the same as if I just took half the interval and doubled it. Okay, that's what this property is saying. Now, an odd function is where you have equal but opposite on one side versus the other. So if this has a region of 4, then you're going to be guaranteed that there is a region of -4 on the other side. And if I were to add up everything on the same distance away from the origin, I'm always going to end up with 0. Okay? If I were to add up the region, same distance on either side of 0. If it's an odd function, this will always occur. Okay? Everything will 0 out. Okay, so let me go through these examples here, and we'll definitely practice with this as we step into our review worksheets tomorrow. Suppose g of x is an even function, so that's a big clue, right? So you know that ultimately, whatever picture you create, you're going to create mirror images on either side of the y-axis. Okay, so that's important. Okay, we have 3 regions here from 0 to 3, from -4 to -3. And then, but what I want us to do is we want to create the full picture first before we look at what we're trying to find. Okay, if we can draw out everything in front of us, then this will feel easy because we're just adding a bunch of numbers. Okay. But here's how I want us to start. Okay, you're given 2 regions that you're going to build, but always start with a shorter interval. I think that is going to help prevent some issues where you're going to see some, because we never want to do overlaps. Okay, our regions will never overlap with each other. So let's start with the shorter interval. Okay, so start with the shorter interval. We're going to build out a region from -4 to -3. And it's going to create a region called 4. So I'm just going to create a region, and I'm going to call it 4. Okay, it's above the x-axis because it's what? It's positive. Okay. Now, as soon as you take care of your shorter interval, go ahead and build out the other side. It doesn't matter. It's not going to make a difference with this problem because this is an easier problem. But as soon as you have that shorter interval built, build out the other side using what you know about that property. So what can I put on the other side just with this knowledge of what we have here? Same thing, meaning that what interval can I put something? 3 to 4. Also what? Also 4. I think this is going to be a useful step down the road. Thank you. Now, from 0 to 3, we have a region called 2. So I'm going to go from 0 to 3. Still above the x-axis. Call this 2. Which means, what can I do on the other side? Also 2 above. Now, you might be thinking, wait, it doesn't really matter if I did it out of order, I still got the same thing, which is great. Okay, but I think if you can follow these 2 steps, it will prevent some issues with the more complicated problems. Now, we're not going to always add everything up. We're going to add up the regions that the problem is asking for us to find. So from -4 to 3, we just total those regions up. What is that equal to? Okay, example 4, same as example 3, but now we want this to be a what? Odd function. So which one do we want to start with? Short interval. Okay. So don't look at the area. Okay. Look at the interval. Right. You want the shorter interval first. That's going to be what's going to be always yeah, it'll be helpful, especially with the next problem. Okay, so I know right now it doesn't feel like a big deal. Okay, -4 to -3. Still +4. But it's an odd function. So let's go ahead and create the property that needs to live on the other side. What's going to live on the other side? -4. Good. So whatever we build on one side, we're going to create equal but opposite on the other side. Okay, now let's go to our second property. Okay, the larger interval from 0 to 3 is 2. Okay, remember, this is still an odd function, so how can I fill out the rest of my graph? This region must be what? -2. Now everything will add up to be 0, which should be the case. 4 minus 2 plus 2 minus 4 is 0. But make sure that you don't just always put 0, because that may not be what the interval is asking for. Right? It's only asking for a portion. So just pay attention to where the problem begins and ends. So from -4, 3. What's that equal to? 4. Okay, let me see if I can squeeze this in. This is the one that is a little more involved here. Okay, even function. 3 to 6, and from -6 to 3, which is the shorter interval? 3 to 6. Okay, so this is the one that we really need to follow this this method that I outlined. All right, let's build out the other side before we explore the second property. What can I put on the other side? From -6 to -3, even, so I also want it to be above. Now, what's strange about this property here? It overlaps a region that's already been established. Okay, so the reason why I want you to build out the shorter interval is help you understand that now this is set in stone. Okay, so if there's anything that you want to add to it, it's not going to add to the region that you have. It's going to add to the region that you don't have already, something that's already not there. So that means I want everything here to add up to be 12. I don't want to do this. I don't want to build this whole thing and call it 12, because this is already 7. I don't want anything overlapping this region. So if this is 7, then what must be the remaining region that will give me this value? 5. So I'm going to put this over as 5. But it's an even function, so what must that mean? They must be split into what? How did I split 5 in half? 2.5. So if you have this shorter interval already built, you're not going to, it's going to be easier for you to recognize, okay, all right, I'm not going to play with that interval. I'm already done, but I do know that there is still whatever remains, 7 plus 5 equals 12. It still matches that interval. And I also understand I got to make it even. So that's how I know to split that in half. Okay, so now from 0 to 6, what's my answer going to be? 9.5. Okay, sorry, I went a little, well, I think got still a few more minutes. You guys have some homework tonight. We'll start our test review tomorrow. Okay, don't get your phones.